Hello, everybody, and welcome to this week's ExoLife Hangout. My name is Tony Darnell. I'm from deepastronomy.space, and today we've got a really good hangout planned for you today, as we do each week, thanks to our good friends at the Planets Foundation. We are going to be talking about Breakthrough Starshot, and you may have heard about this. There was a big press release about this. I guess it was sometime last year. And these guys are planning to send hundreds of gram-sized spacecraft to the nearest star, Proxima Centauri, which is 14,000 light years away. And for those of you who deal with miles, that's something like 25 trillion or so miles away. And once these little gram-sized spaceships get there, they're going to take a picture, and they're going to try to contact Earth, and maybe send some pictures back not only of Proxima Centauri, but the exoplanet in orbit around it, Proxima b, which we've talked about many times on these hangouts. And so today, we have Dr. Avi Loeb with us, and I'm very excited to talk to him. He's the chair of the Astronomy Department at Harvard. He's also the founding director of the Black Hole Initiative, something I want to talk about, too, at some point. What the heck that would be, and what kind of fun. I mean, that just sounds fun, the Black Hole Initiative. And he's also chairing the advisory committee for the Breakthrough Starshot Initiative. So without any more ado, let me pull up my big screen where everybody's visible. Hi, guys.
Hi.
All right, so let me just introduce everyone. In the lower left is our guest, Dr. Avi Loeb. He is the guy I was just introducing. In the lower right is Dr. Jeffrey Kuhn. He is he's a member of the Planets Foundation and also a solar physicist and lots of other really cool things. Hi, Jeff.
Hi.
There you go. Okay, yeah, wake up. We're here. And also is Kevin, up in the upper right is Kevin Lewis, who's helping me drive the hangout and looking at the chat and all that other kind of fun stuff. So anyway, here we go. I was playing with this before we started, and I hope the sound is going to be good enough from my microphone. I was worried right before the hangout I started to hear an echo, but I think I got rid of it. But I trust you guys will let me know if you still hear things. Lots of people on live chat already. I'm seeing Thomas Martin Newson, that's a new name, as well as Barsabas and Toxic Vamp. I remember that one. Capital H is back. Welcome. Echo when you went to your guests. Okay, let's see here. Hopefully it's not still there. If it is, I'll have to mess around with it. But anyway, okay. So Avi, since I would like to start with you and have you talk a little bit about what got you involved in this initiative to try and go to the nearest planet in our galaxy?
Well, I had some early conversations with Yuri Milner. He was mostly interested in finding evidence for life elsewhere, and that's fundamentally a very basic question that all of us wonder about. I find it to be the most exciting question in science because it has huge implications. If we find evidence for life elsewhere on other planets outside the solar system, it will change our perception about our place in the universe. It will affect world politics. It will affect religion. It would affect sociology, linguistics. You can imagine a lot of subfields growing out of astronomy, like astro-linguistics, how to communicate with aliens if we find them to be intelligent, how to understand biology with different chemistry, how to contemplate the resources that are out there in space, including information. You know, if this civilization is much more advanced than we are, we will learn a lot from them. We'll have a jump start, depending on when they started thinking about the problems that we are now encountering. And so this is clearly a very fundamental question. Are we alone? And Yuri was consulting with a number of people in the community. I was one of them. And then at some point in May 2015, he showed up in my office and asked me whether I'm willing to lead an initiative that is aimed to visit the nearest planets and perhaps take photographs and send back photographs within our lifetime, within a few decades. And of course, the nearest star to Earth is about 4 light years away. So if you want to reach it, let's say within 2 decades, both Yuri and I are 55 years old, So within our lifetime means 2 decades. If you want to do that, you need to launch the spacecraft at a fifth of the speed of light, at the very least. And so I told Yuri at that point that I'm very excited. It didn't take me much time to agree the entire concept. But what I wanted to figure out is whether there is a technology that will allow us to do that. And I told him I need at least 6 months to do so. And then with a group of students and postdocs, we looked at all possibilities that were suggested over the years and also other possibilities that were not suggested. And we reached one conclusion, a simple conclusion, that there is only one technology that seems in principle feasible at this point in time. And then at the end of 2015, just before New Year's, I got a phone call from Pete Warden, who is he's the director of, or the executive director of the Breakthrough Foundation. And he asked me to make a presentation at Yuri's home about the recommendation of my group. And I had just a week or so to prepare it. And we were just about to go with my family. My wife said, why don't we spend the weekend? We were in Israel at the time. Why don't we spend it in a goat farm? So we were just about to get into the car when he called me. I got to the goat farm and I had to prepare my talk, but there was no connection to internet. So the only connection was actually next to the reception, which was sort of a building, an office building. So I sat at 6 a.m. With my back to the wall of the office, of this office, looking at the goats that were just born the day before and preparing my slides, contemplating the first mission to visit the nearest star. That was very surrealistic. I'm sure that the farmer that owned the goat farm never imagined that, the first realistic mission will be contemplated there. And then we presented it to him a week later, and he was excited. Now, I told him, look, there is not there are not many technologies that one can think about. This is the only one that seems realistic. But I told him it's just like getting married. You just need one solution to your problem. You don't need more than that. And so we should be very happy that there is this possibility. And the idea was to basically push a sail with a laser beam. Just like the sail of a sailboat is being pushed by a wind, by the molecules of air bouncing off, you can imagine the particles of light, the photons bouncing off a sail and pushing it. And the advantage of that is that you can reach close to the speed of light because you are pushing it with particles of light. And the reason it's in principle feasible nowadays is especially because the spacecraft can be extremely light. We now have materials that can make a sail that weighs of order a gram with a surface area of a few 10 meters squared or so. And then also laser technology has developed to the point where we can imagine very powerful lasers that combine together to make a beam of order 50 gigawatt, which is roughly the power that was needed to lift the space shuttle. And you need to provide this power roughly over 2 minutes, a few minutes. So the amount of energy needed is roughly the energy needed to lift the space shuttle, except you give it to a single gram of material, and then it reaches a fraction of the speed of light. Now, following that, we worked very hard. There were many discussions that lasted, many hours with Yuri, Pete Warden, and Pete Klupar, who is the chief engineer for the project. And we spent, I would say, of order 50 hours discussing the concept. And Yuri was mainly interested in showstoppers, other issues that that basically block any progress. And we couldn't find any. And then we came with a public announcement in April 2016. And then following that, there was an advisory committee that was established that includes about 35 distinguished scientists, one of which is Jeff Kuhn, that is here on the panel. And we meet regularly, roughly twice a year. And it looks like the next phase, which we hope will take place within a couple of months, will be to solicit the proposals from experimental teams where we will start to test the feasibility of the technology. So the next 5 years will be dedicated to the feasibility study of the technology at a cost of over $100 million, to which Yuri committed. And then if the technology seems feasible, we will move on to the next phase, which will be 10 times more expensive, where we will build a small-scale demo, a demonstration of the system that includes both the laser and the sail, just to show that we can accomplish an acceleration at the principles of this technology are being demonstrated. And then the next phase after that will be, again, another order of magnitude increase in funding to build the real system. And so that's, roughly speaking, the layout of the project. And of course, we are now focused on the first 5 years. And I should say, this is a very unusual experience for me, because I was practicing astronomy for 3 decades now. And I'm a theoretical astrophysicist. I started most of my work early on was in cosmology, the study of the universe at large. Then I moved on to work on black holes, and we can talk about that later. And more recently, I shifted to work on the search for life, both primitive and intelligent life. The search for primitive life is very much part of the mainstream in astronomy right now. For some reason, the search for intelligent life is outside the mainstream. I don't see a simple reason for why one should discriminate between the two. I think we should search for both. Because intelligent life, in principle, can send signals that are much brighter, and therefore the search volume can be much bigger. So even though it may be rarer, some people believe that intelligent life is much rarer because they prefer to feel special, as intelligent beings.
No, it's not necessarily. Now, hang on. Just because I happen to think that life is special as far as that goes.
Well, it's a very precious thing that we have, but
I don't mean just precious because we're alive. I mean, I think it's actually harder than we think it is to have life and intelligence.
I should perhaps lay out my philosophy from the start. I think we are not special, okay? And the reason I arrived at this conclusion is, people from the start thought that we are at the center of the physical universe, that the Earth is at the center and the sun is moving around it and the universe at large, all the stars. Then we found out that we are not at the center of the physical universe. I think the same applies to the biological universe. And it's very natural for people to think that we are special. It's very natural because I see my daughters, and when they were young, they thought the world centers on them. But as they grew up, they matured. And I prefer to be in the matured state to start with. So in other words, let's start from the hypothesis that we are not special. If it turns out to be wrong, then I would accept that perhaps we have something special. But I think that the starting point should be that we are not special, and therefore primitive life and intelligent life is ubiquitous. It's out there. We just need to find it. And, just like LIGO searched for signals, gravitational wave signals from black hole mergers, and didn't see anything for, a long time. And then once they pushed the sensitivity below a certain threshold, they are seeing one event per month. And I think the same applies to the search for intelligent life. I think that once we reach a certain threshold, we will see a lot of signals coming at us. It's just that we haven't reached that threshold.
Okay. Well, I let you go and basically you said everything. You gave all the punchlines away. You said everything. So now we're done, guys. We'll see. That was our whole hangout. No. So we're going to go back and visit a lot of the things that you just picked at. Okay, guys, I'm going to stick to the Brady Bunch look. Make sure, see if I've got an echo here. I'm going to get rid of the other shots. I don't know what's wrong with it right now. I can't troubleshoot it. Okay. So now you mentioned some of the other things you were working on, and when I was doing my introduction of you, I wanted to read these, and I didn't do it, so I'm going to do it now. Avi has written several really cool books. One of the books is The First Galaxies in the Universe, which I would love to have an entire hangout to talk about that. But he also has written a book, a series of stories or essays called From the First Star to Milkomeda. I always call it Milkomedia, but anyway. And folks, I put the link to that. It's on Amazon. It's a Kindle book, and I put the link to that in the description box of the Hangout. So check it out. I've already downloaded it on my Kindle. I haven't read it yet, but I just want to let you guys know he does have a lot of great things. Now, Jeff, he mentioned your name. He implicated you in this. Why don't you tell us how you're involved as well? Remember, he said you were one of the people that were.
Oh, I'm.
Oh, your audio's terrible.
I'm still in the minor leagues. My involvement is through this concept related to. I have a bad internet connection.
I know.
Can you hear me at all? Video is
yeah, we
lagged,
can hear you, but your video.
I'm not
you,
sure.
You might want to maybe freeze your video and then just use audio. I'm not sure. Boy, I just love this. Okay, good. Well, all right. We'll come back to you as well as that, on that one, Jeff. Okay, so Avi.
Hear me now?
Yes, that's good. Go ahead. Go ahead, Jeff.
Okay, so I'm going to represent myself with 4 letters.
Yes.
I think that the best thing that's going to come of the Breakthrough Foundation is I'm hoping that we are going to actually get there. But the technology and just the open attitude towards solving these problems is fantastic. And I've never been with a group of scientists that have had this open mind towards, we're not violating any laws of physics. You've established that. We're okay with the laws of physics, and so it's going to be great. And what comes out of it is, I think, it could very well change the way we think about all of life here on the Earth. We're going to find our place in the cosmic think, but I think it's going to happen in ways that we don't yet think, and that's the exciting part of it.
All
so
right.
Stay tuned.
And so when you are interacting, I want to talk more of some more specifics in a minute about what Breakthrough Starshot is up to. But are you just watching peripherally, Jeff, or are you actively engaged in helping talk about where to go, what to do exactly?
My job is to convince this group of scientists that they need a really big telescope.
Is that a plug for the Planet
because we have to. No, not exactly. But part of the problem is we have to be able to sense the signal that comes back from this satellite, and this obvious described.
Oh, okay. Oh, Jeff. Oh man. Okay. Well, we're getting like every third word, and maybe that
issues that we have to look at. One of them is the telescope. It's the telescope.
Yeah, I'm sorry, Jeff. We're just not getting you right now. I know. All right. So, Kevin, would you please put up that image of the little spacecraft that they are thinking about sending up, and then I'll have Avi maybe talk about some of the components on this thing. Now, these are about, as I understand it, Avi, correct me if I'm wrong, these are about a gram or so. These are little tiny, basically little postage stamps that you're sending out, correct?
In fact, what you're looking at right now, these are the first examples that were launched into space, and it was announced today, actually, in a press release, that these are called sprites, or small chips that include some electronics that were sent out to space. And just to demonstrate that they can survive the launch, the electronics can survive the launch, and then survive the harsh environment of space and can communicate with Earth. This particular project was led by Zach Manchester, who started it during his PhD at Cornell University. He's now a postdoc at Harvard. And there was just it should appear in the news today. I mean, you can check out. These are called sprites. They are small chips. And they are sort of the first demonstration of the technology. So the reason this technology makes sense is we can now pack electronics into a single gram, including a camera, a navigation device, a communication device, everything we need. Sort of like the guts of an iPhone without the case and the human interface.
It looks simpler than that even.
Yeah, this one has actually the biggest component is actually the solar panel that collects light. And there are these whiskers, which are just radio antenna. In the actual Starshot mission, we might actually etch the electronics on the sail, in the inside of the sail. So the sail is supposed to reflect the light. It's not supposed to absorb any of it. So the absorption has to be less than 1 part in 100,000 of the laser light, because otherwise it will burn up. The sail will disappear, sort of like the wings of Daedalus. I mean the story. Icarus. Sorry. And so the idea is that it will be the material will be such that it reflects almost all the light that on it. And then in the inside there would be the electronics. Now there is an interesting question of what design should one give to the sail. Should it be a parachute-like design or architecture? The answer is no. We actually did the analysis with Zach in a paper that we published a few months ago, where we showed that it's an unstable configuration. A parachute that configuration can slide easily off a beam. And so a much more stable configuration is having a hollow laser beam that has sort of a hole in the middle, looks like a cylinder, and then making the sail spherical, sort of like a giant ping pong.
Okay, yeah, I want to go back to both of those points, but I want to go right back to this spacecraft again, which looked like to me something that you would build, like you could get a little kit and you could have a soldering iron on there and you could just make it. I just want to go back to this. I'm seeing a radio. I see a magnetometer of all things, something that measures magnetic fields, a gyroscope, which I get. Solar cells I get, microcontroller I also get, and that antenna looks awful tiny, but I'm not seeing a camera.
No, there is no camera on this one.
But the one you're planning on going out to send would have.
Yeah, we plan to put a camera, but by the way, the miniaturized electronics is almost available now. I mean, we can pack everything we need into a single gram, less than a gram. There is, as far as we can see, there is no major obstacle in that sense. The big challenges are in the context of making the sail of a material that reflects 99.999% of the light.
Okay.
Constructing a laser beamer, which is composed of many small lasers that combine their beams into a coherent laser beam, that passes through the atmosphere. You have to make corrections to distortions of the phase of the laser beam and maintain its focus on the sail that is outside the atmosphere. The sail itself is released from a mother spacecraft above the atmosphere, and the laser beam is supposed to push it when it's at the right location. And we expect to launch one per day, and these spacecrafts are extremely cheap. This sprite that you see in the picture costs a few tens of dollars. It's really cheap. So the idea here is, unlike previous space missions where the spacecraft was extremely expensive, it took decades to build them. Here we're talking about miniaturized electronics on a relatively cheap setup. And we can launch many of these. There would be a fleet of hundreds of them.
I get that you're not worried so much about the spacecraft. I mean, you're right. At JWST, it's not. But I mean, I just wanted to talk about that very briefly and then move on to the other things. But just that solar panel and the antenna, that's the only power supply that it has once it's there, correct? Once there's no batteries or anything.
Yeah, no. Actually, okay. So this is. These are the chips that were launched to space recently, and you needed those components. But In terms of Starshot, there will be actually, once you launch it to a fifth of the speed of light, the friction with the interstellar medium, the ambient gas in the space between us and the nearest stars, just the fact that there are protons and electrons impinging on the wall of the spacecraft will charge it, because the electrons that are colliding with the wall will eject electrons from the wall out of the spacecraft, and then the spacecraft will be positively charged at the front, and it will also be hotter at the front than in the back, and you can use that as a battery to power everything that you need on the spacecraft. So it will not be a solar panel that is powering it. It could be just the temperature difference between the front and the back, or the charge, just like a battery. There will be a positive charge in the front that can drive a current. Of course, you can supplement that with radioactive material that will provide additional power. But what I'm saying is it will not be the same design as you see in this small chip. These chips were just launched above the atmosphere, and they're just floating there, and they need power from sunlight.
Okay. So you were saying that early on, you and Yuri were talking about this for like 50 hours and getting your plans put up, and you guys were discussing, and he seemed, and rightfully so, I would imagine, really interested in talking about the challenges, and you've already alluded to what they are. You've said that the big issue here isn't these little tiny gram things. They're pretty simple to make, and they're pretty straightforward. It's the other things. It's the lasers and the light sails. Now, we have done, let's start with the light sails. We have done some work. I mean, by we, I mean humans, and by humans, I mean specifically the Planetary Society and a few other people have actually tested light sails. These are, and I want to go back and explain what they are for people who may not know. They are these giant, very thin mylar-looking things. They may not be made of mylar, probably aren't, but they are designed to be pushed to take a large area, so that they can gather as many photons as they can, and the radiation pressure from those photons pushes that sail, which pulls whatever the payload is. In this case, these little 1 gram things. Now, and you were saying that you guys played around, so that we've tested this and it works as a concept. But you're saying that you're going to need, and you've, and please clarify this, because I just want to make sure I don't miss it. You're saying that the shape that really works well for the light sails is a spherical one, a ball?
Yes. Now, I should preface this by saying, this is the entire concept of pushing a sail with a laser beam is not new. I mean, shortly after lasers were invented, Bob Forward wrote a paper about it in 1962. And there were a few papers written in the 60s, published in Nature, talking about, light sails with lasers and so forth. And most recently, it was Phil Lubin that wrote an extensive paper on this concept, emphasizing the fact that the technology has evolved since the 60s, and now it may be feasible. So there is a long history. And as you say, this idea of a light sail was demonstrated. There is actually a project called Icarus, Japanese project.
Oh, that's right. I forgot to mention them. The Japanese, it's JAXA. I forget the acronym.
That's right.
But it's JAXA, the Japanese Aerospace, Japanese Space Program.
Right. Mm-hmm. Now, so the demonstration was using sunlight. And when you use sunlight, the flux of light from the sun declines as 1 over distance squared. So most of the push that you get to the sail, if you have a sail of a fixed area, you're collecting less and less light as you move away from the sun, like 1 over the distance squared. And as a result, most of the push is actually at the starting point. Because roughly speaking, you get to a speed that is dictated by, that is proportional to 1 over the initial distance, okay, just roughly speaking. So obviously, depending on where you start, you get to some terminal speed due to the sun. Now, with a laser, the situation is quite different because you are focusing the light on the sail, and you have a certain distance over which the beam, the spot of the beam is tailored to fit the sail size. So there is no decline with distance of the amount of energy that is impinging per unit time on the sail. And also you're putting much more power, much more energy per unit area on this sail. So we're talking, and the reason we have to do that is because we want to reach a fifth of the speed of light within a few minutes.
That's right, 20%.
With the sun, the most you can get to is of the order of 500 kilometers per second, which is 1/1000th, a tenth of a percent of the speed of light.
Yeah, it's fast, but you're not going to get there anytime soon.
A factor of 100 less speed, and that's if you start really at the surface of the sun, which is obviously ridiculous because the wall of this or the sail itself will melt. But you can't reach more than 10 to the power minus 3 of the speed of light with using sunlight, okay? And just because that's the kind of speed you reach from the surface of the sun. So obviously, I mean, the technology, I mean, the idea of a light sail can be demonstrated with sunlight, but if you want to use a laser beam, the design has to be different, and in particular, you are putting much more power. Now, there is a question, when you have a collimated laser beam, what would constitute a sail that rides in a stable way on the laser beam? And you need to do a stability analysis, and we found that an umbrella-shaped sail or a parachute-shaped sail is unstable unless the payload is very far down from the sail, so that the center of mass is away from the sail. But that's difficult to do because then the payload will burn because it will be in front. It's actually very complicated. So what happens to be a very ideal configuration is a spherical one, and we show that it will be stable, at least based on the analysis we did. One can do more sophisticated analysis. So you can imagine like a ping pong ball, which is held in place by a hollow beam, a beam that has a less power in the middle, and it can be pushed all along in a stable way. And so that's the design we came up with, and the advantage of that is that you can put the electronics in the middle, and it's protected as long as the light doesn't get
So
through.
there's a hole somewhere, though, in the sphere.
No, there is no.
It's just pushing against the sphere.
Yeah, and you can inflate the sphere in space. You can start just like a balloon. You can make up the sail to have the right size. In principle, you can do it in space just by pumping gas into it. And the pressure of the gas will hold it together, sort of like a balloon. You can imagine it this way. Right. But I should say, these are early times. You know, we just came up with this concept a few months ago in a paper we wrote with Zach Manchester. There is still work to be done. And the next, the next phase will be actually to figure out what are the best materials, what's the best design. So there would be, 5 years worth of work going into that. And if you speak with me in a few years, I'm sure, I'll have more details.
Oh, you can count on it. I'd love to. Yeah.
So it's work in progress. That's the way to think of it.
Okay. Well, all right. So the sphere is what you've come up with is the best shape for the sail. And I want to go back to what you're talking about with the laser, because I know these two one doesn't work without the other. You need the other. So the laser now, anybody who's played with a laser pointer knows that they're a pencil thin beam of light. But even so, they still kind of spread out a little bit. You mentioned something called a collimated laser, which is something that keeps it from doing that even more. You don't want the laser beam to spread out at all if you can help it, because like you say, you want this radiation pressure from the laser beam to be as strong as it needs to be. Now, I have two questions. One is, can you repeat how powerful the laser needs to be? Because you said it at the beginning. And my second question is, how big around is this laser going to be?
So our design is to have a laser of the order of 50 gigawatt, maybe up to 100 gigawatt.
50 billion watts.
Yes. Focused on a spot with a size of a few meters. So that's roughly the diameter of the sail, or the radius of the sail. The exact numbers depend on what terminal speed you want to achieve and on some optimization. But we're talking about a few meters in size, a spot that is a few meters in size, across a distance of a few million kilometers. So that's the launch distance. So it's 5 times the distance to the moon. That's the distance over which you can keep the laser beam collimated.
How many, now, say it one more time. How many kilometers?
A couple of million, a few million.
A few million, okay. So
yeah, and we're talking about a wavelength of order 1 micron. That's
that was my third question about the laser.
So
the infrared laser.
Yes, because the atmosphere transmits at that wavelength. And the array of lasers, so the laser beam is composed of many small beams that come together in a coherent fashion. We're talking about a kilometer square, roughly an array of order a kilometer in size. So the wavelength of the light divided by the size of the array of lasers gives you the collimation angle. It's called the diffraction limit of such an array, is what I refer to as a few meters over a few million kilometers. Of course, you can tailor electronically, you can tailor the beam of the laser by changing the phase of the different lasers. And the idea is to correct for distortions due to the atmosphere. The atmosphere has turbulence and it distorts the phase of the wave. And we can correct for that. That's one of the big challenges, to correct for that. But you can also tailor the beam of the laser by appropriately designing the phase of the different small lasers that combine together. And you can also make the beam such that it will always have the size of a few meters over the few million kilometers, irrespective of where the sail is. So you can sort of make the beam a little bit broader when the sail is closer to the ground than when it's farther away.
Okay. Wow. So I'm still, okay. So the, when it comes to the, I just want to give people, first of all, this few million kilometer distance that he's talking about. Many of you know about JWST. It's going to be put at the L2 point. That's 1.5 million kilometers away. We're looking at several times further than that. That's its initial push. That's its only push. Right? And that's enough for the acceleration to get from 0 to 20% the speed of light.
Yeah, I should give. I'll give you a formula that is very helpful in this context, which I found to be a very interesting coincidence. If you take an acceleration of 1g, okay, the acceleration that we feel on the surface of the Earth, 1g, and you apply it over a period of 1 year to an object, the object will reach the speed of light. So 1g times 1 year, an acceleration times time, gives you a speed. Turns out that 1 year times 1g equals the speed of light, c. So that allows you to figure out. So if you want to reach the speed of light over a shorter period of time, you need a higher acceleration. If you want, for example, to have a spacecraft that is very massive, like we see in science fiction movies that carries people. We know that pilots, they can survive, fighter pilots can survive maybe 10G, but not much more than that. Their body would be crushed. And so suppose you want people to feel comfortable. You put them on a spacecraft that is moving at 1G, okay? It would feel just like being on the surface of the Earth. You wouldn't feel any difference. According to Einstein, gravity is equivalent to an accelerated frame, so it doesn't really matter. You will sit in this spacecraft and you will feel as if you're on the surface of the Earth at 1G. And if you apply that for 1 year, that spacecraft will reach the speed of light. You can imagine an advanced civilization that reached this milestone. They already mastered this technology of light sails, and they can, in principle, lift very massive spacecrafts at 1G using a very powerful beam of radiation. And I actually, after being involved in Starshot, I started thinking about it. How would we see, what would the signal look like if there was a beam of light like that? Since the source is moving relative to us, this beam will sweep across the sky and we would see it as a flash of light. So I was asking myself, is there any flash of light that we see routinely that we don't have an explanation for? And the answer is that there are these fast radio bursts. These are very short
those, yeah.
bursts. And so we wrote a paper where we tried to analyze what are the requirements for a system that will produce the fast radio burst. and could it be related to a light sail propulsion system? And we published this paper in the Astrophysical Journal Letters, I should say. And when people ask me, okay, I mean, obviously this is a speculation. This is not something that it's just a possibility. What I say is that it's important to put all possibilities up front, so that if in the future we could rule them out, just like a detective does when there is a crime scene and the detective wants to figure out who the criminal is. If we don't have an explanation as of yet to fast radio bursts, it's worth considering that. If these are not related to light sails, perhaps some other phenomena that we will find in the future will be related. So, it's worth keeping that in mind, that if we see flashes of light, they could be related to light sails from other civilizations.
Wow, that's an interesting idea. Okay, well, I want to get to some of our questions, and David Sims has one that I've been thinking about, and I've been wanting to ask you, but I'm going to just have his words do it. He's saying thermocouples taking advantage of friction with the interstellar medium. My question is, I want to know. Actually, I don't understand what your question is, David. So I'm just going to ask you flat out about friction in the interstellar medium. I mean, yes, you've got, it's not totally empty. You've given it a good push. But what about other things between here and there?
That's a very good question.
Is that going to have an effect?
That's one of the challenges that we put. I mean, we came up with about 20 challenges, and actually, Yuri went around the table before the public announcement and asked people, "What do you think is the biggest challenge?" I personally thought that the biggest challenge is the sail, making sure that it doesn't burn up. But other people suggested perhaps dust, because if the sail collides with a dust particle along the path, that could cause the destruction of the spacecraft. And so we actually wrote a paper about this with 2 postdocs and a senior person, where we analyzed the risk from dust. And what we found is if you take the distribution of grain sizes in the interstellar medium that we know about, and the distance to the Alpha Centauri star system. So Alpha Centauri has 3 stars, Alpha Centauri A and B, and Proxima Centauri. And Proxima actually has a planet in the habitable zone. Now, we know roughly how much column of gas and dust there should be, with some error, uncertainty. We know how much there should be on the path to Alpha Centauri.
Okay,
and
I was going to ask you that. How well do we know the interstellar medium between here and there?
Within a factor of a few, we know it. And one thing to point out is the path to the future location of Alpha Centauri, and we should keep in mind that we need...
The galaxy rotates, doesn't it?
where the Alpha Centauri system will be in 20 years. It's not the place where... We are not shooting at Alpha Centauri right now, because we are moving at less than the speed of light. And so we need to figure out where it will be in 20 years and shoot it in that direction. That direction is not in the plane of the planets. It's not the zodiacal plane where the dust in the solar system lies. So we're shooting it at an angle relative to the plane of the orbits of planets in the solar system. But we did calculate, and we found that if you just put a coating of roughly 1 millimeter in front of the spacecraft, that should be enough to protect it. Every dust particle that collides with the spacecraft produces a crater, because if you go to the rest frame of the spacecraft, you have the particle moving at 1/5 of the speed of light. So you release more energy than a nuclear explosion per unit mass when a particle collides with the wall of the spacecraft. So it's actually could be very damaging. If the particle is more than 1 micron, if it's 10 micron, it could actually destroy the spacecraft. But 10 micron dust particles are extremely rare. And so we did the calculation. We found that it should be relatively safe if you produce a coating that is roughly 1 millimeter in thickness, and that will protect the spacecraft.
All right. Maple Flavor is going back to your radio bursts, your fast radio bursts, and asking, would this be perceived as a fast radio burst from an outside observer, presumably your laser?
Yeah, so fast radio bursts are observed in the radio regime at a wavelength of the order of 20 centimeters. And then one of them, at least, we know the distance to, and it's roughly at the edge of the universe. It's a gigaparsec or billions of light years away. Okay. Now, we did the calculation and we found that the amount of power that needs to be emitted by the beamer, if you imagine it being associated with a Starshot-like project, the amount of power is roughly the power that is intercepted by the Earth from the sun. Okay, so that's an interesting coincidence. If there is an advanced
that is
that is using all the power impinging on the surface of its planet,
50 gigawatts,
beaming it in radio waves, that would be it. I should mention that this is called Type 1 Kardashev civilization that is using the power impinging on the surface of the planet. Type 2 is using most of the power from the star, which is much more than that. And Type 3 is using the power from the galaxy.
Okay.
You may ask, why radio? Because I was talking about the infrared before. If you want to launch a spacecraft at 1G, rather than at 60,000 G, which is the acceleration that Starshot is aiming at. If you imagine lifting humans or creatures that can only tolerate the acceleration on the surface of their host planet, their parent planet, then it turns out that the radio is the best frequency, the best wavelength for low accelerations, 1G. It's the optimal wavelength.
Okay.
I mean,
it's something that presumably wouldn't kill an organic person or a biological unit that might.
Well,
be...
the issue, yeah, in order to, what you need is a very long distance of acceleration, because as I said, it takes a year to reach the speed of light at 1G. So,
I love that. I never heard that rule of thumb. I love it. I'm going to use it all the time now.
so given that large distance and the need to focus the beam and so forth, if you take the acceleration into consideration and the distance over which you need to accelerate it to reach the speed of light, you find out that the wavelength of 20 centimeters or so is actually the optimal wavelength. And we talk about it in the paper.
Okay.
So this could explain why these are radio bursts and not infrared bursts. Of course, most astronomers would argue that it must be some natural source. It needs to be maybe a neutron star that is newly born and has some very strong magnetic fields. But I should say that you cannot emit these fast radio bursts from a hot surface, because the surface would need to have temperatures of 10 to the power 36 degrees Kelvin, extremely high. You need to have some coherent process that emits. So in a radio antenna, you get coherence of the emission because you move a bunch of electrons back and forth in the antenna, up and down, and that's how you get very powerful radio emission. That's called coherent emission because all the electrons emit in phase with each other. The same thing happens in a laser. You get emission that is coherent. All the atoms are emitting the photons at the same phase. And so you really need a coherent emission mechanism to make those fast radio bursts. And it's not trivial. We know that pulsars do that, but they are roughly 10 billion times fainter than these fast radio bursts. Fast radio bursts are 10 billion times brighter. So I should say that if a fast radio burst takes place in our galaxy, instead of being at the edge of the universe, like most of them, if it turns out to happen in our galaxy, and our estimate is that it should happen every 100 years or so, then you could detect it with a cell phone. It's that bright. It's roughly 10 gigajansky in brightness, because the typical radio burst is 1 Jansky from billions of light years away. If you put it in our galaxy, it will be 10 gigajansky, and you should be able to detect it, with a cell phone.
Okay. All right. So Toxic Vamp and Space Dude are worried about pointing this laser at another. At a Space Dude is like, what if we get invaded because of this? And Toxic Vamp is like sharing lasers in aliens' eyes could spark an intergalactic war. So basically, the while this is bright near its source, it will only be going out a few million kilometers anyway. So by then, looking into the laser isn't going to hurt you beyond that.
Well, it's not so much the fact that it hurts, but this is a valid concern about the fact that there would be some leakage of the radiation that could, in principle, be observed by another civilization. It really depends on whether you believe that intelligent civilizations out there, if they exist, are hostile or friendly, because my perception or my hope is that once we launch Starshot, we will get a signal, a radio signal, or a SETI signal that says, "Welcome to the Interstellar Club," because that will be the first time that we are actually admitted to interstellar travel club, and it's quite possible that there are lots of spacecrafts roaming through space. They produce very weak signals. It's very difficult to see them. By the way, if we can ask Jeff. I mean, if there was a spacecraft roughly of 1 gram passing near the Earth that was picked up by a telescope, and it's not easy to see it because it has a very small area. Even if we saw it, it would move so fast that the observers would say, "Oh, it's a cosmic ray, it's some fluke." They would completely dismiss it. And so it's quite possible that these things are flying out there, but we haven't yet noticed.
Jeff, you want to give it a try? I hope your audio's good.
I'm in a hotel in Montreal, a long way off, even a foreign country, and so I don't know. Can you hear me?
Yes, you're good. So far, so good.
No.
Yes, you're good.
Barely.
No, you're good.
Okay, so I think that this raises a really interesting question, which is this is all about remote sensing, and so we're converting the remote sensing problem of seeing the surface of the planet into the remote sensing problem of seeing the nano probe, and I think Avi shared his vision of what the greatest challenge is. My vision of the greatest challenge is to be able to see the nano-craft from the distance of Proxima Centauri or Alpha Centauri. But of course, you're right. These probes zipping through the solar system, I don't think. Well, of course, it would be catastrophic if they aimed wrong and they ran into the Earth. I can't remember that calculation, Avi. Maybe you do. But if we miscalculate and we dump one of these onto the surface of a friendly planet around Proxima b, it's a thermonuclear explosion, essentially, in terms of...
Yeah, but it's only, we're talking about a few grams. So it's similar to an asteroid impact in terms of energy. It's not really...
In terms of energy.
Yeah, it's not unusual compared to the fact that asteroids are hitting such planets all the time.
Except it's at 20% of the speed of light, which is a lot of energy. But I think it's a remote sensing problem, and we would, if we could look at, because it's relativistic, if we could look at some of the, I think of course, when they come through the environment of the solar system, the density of particles is much higher, and I think we could begin to see some of that friction that Avi talked about, the energy that it sheds as it passes through a charged environment, leaves a wake in the interplanetary medium that might be interesting.
Yes, that's an interesting point.
How many watts do these things presumably put out? I mean, what kind of signal are we talking about here?
Well, what Jeff is discussing is the fact that there would be a bow shock, just like, when...
the bow shock of the solar sail or of the little tiny gram? Or
okay,
I should
explain that, the solar sail, the sail itself initially is open so that it will intercept as much of the laser beam as possible. But then once the launch is finished, we might either discard it or fold it, because
I didn't hear that part. Okay.
You want a needle-shaped configuration to minimize the cross-sectional area, because you don't want much friction with the surrounding medium until you reach the planet that you're aiming at. And so But nevertheless, there would still be some effective cross-section to this needle-shaped spacecraft. And the fact that it's charged would introduce a wake, just like the wave that is produced by a boat moving on the surface of a lake.
The EM field of the spacecraft itself would produce a bow shock. Yeah.
Now, this you could get some emission of light from that, but it will be very low power. It's really difficult to detect that. And I think
things get so interesting at relativistic speeds, don't they?
Yeah. Well, actually, you might think that when you take a photo, you might think because of Lorentz contraction, Einstein's special relativity, that the photo will be squeezed in one dimension along the direction of motion. But actually, there was a paper back in the 60s by Terrell that calculated what happens to a relativistic camera when it takes a photo. Turns out that because of time dilation, the photo would look, if you have a circular planet, the image will stay circular. And one way to think of this is that the speed of light is independent of your motion. So the fact that you are moving in one direction doesn't change really the circular shape of the source. The source will be actually oriented slightly differently. So there would be some aberration. The angles which will change, but it will still be circular. So the fact that you're moving relativistically doesn't change the shape of the object.
Oh, okay. Well, Galaxia and I have the same question. I'm going to ask Galaxia's question. She goes, the technology has to be developed to shoot a beam at 50 billion watts. How far away are we getting from making a laser like this? Where are we in laser technology right now?
Okay, this is so the idea here is to use many small laser beams. Okay, and question is how powerful should each beam be? And we are thinking about either 100 kilowatt or a megawatt, which is 1 part in 100,000 of what we are aiming in total. So we're talking about 100,000 lasers or 1 million lasers, depending on exactly how much power we give to each of them, spread over a kilometer size array. So you have, let's say, 1 million such lasers, and you combine their beams. Now, how close are we to getting 100 kilowatt laser? We're actually getting very close to that. We definitely have 1 kilowatt and 10 kilowatt. We're getting close to 100 kilowatt per.
So we're in the kilowatt unit range right now.
We're getting there. Now, okay. The main issue here is when you have a lot of these units, you need to demonstrate that you can combine those beams into a coherent single beam, such that you.
And that's the collimating part, right? That's the part.
Yeah, and that's non-trivial. That's what we need to demonstrate in the next 5 years.
Okay.
But in terms of a single unit reaching the power that we need per unit, we are not far. Now, the other thing to keep in mind is the cost. We need to bring the cost down such that this project will be feasible. And one way to bring it down is by manufacturing many such units. And it's quite possible that Starshot would be the prime driver for bringing the cost down, because we would need many more lasers than the consumption right now in the market.
Okay. And infrared lasers have a lot of use too in other ways, but that's a good point. Okay, so Larry Keese, now we talked about the interstellar medium. You say it's not a big issue if you add 1 millimeter of material around the solar sail or material around something. I forgot. I think it was a solar sail that would protect you from most of the collisions you might have. But what about the magnetopause and the heliopause? It affected Voyager, for example, right? I mean, it was a non-trivial, non-zero effect. Is that something? Because it doesn't matter that you're out of the plane of the solar system. I mean, it's all kind of there.
Yeah,
right?
But what you need to realize is what the calculation we have done depends really on the column of material. It doesn't matter how spread. So you just need to know how many particles you have per unit area that you are sweeping, okay? Now, if you take these particles, put them in a thin slab, or you spread them over a large distance, doesn't matter, because overall you will intercept, you will collide with a certain number of particles. It doesn't matter if you collide with them over a short time scale or a long time scale. Now, the way to think about the shock wave at the edge of the solar system, the heliopause, is that basically there is the solar wind, which is collecting material along the path and concentrating those particles in a shell around the solar system. But the fact that it sort of condenses them into a shell doesn't really matter, because you would intercept these particles anyway. And what matters really is how many particles per unit area you are intercepting along the path to Alpha Centauri. Whether these particles are packed in a thin slab or whether they are spread and the solar wind, didn't pack them together, doesn't really matter. You have the same number of particles. And so there is no threat from the number of particles in the heliopause. The only other issue that could come into play is the magnetic fields. That maybe because the spacecraft is charged, it can be deflected by magnetic fields. It's just like a charged particle that can be affected. So it's not only gravity that is affecting the motion of the spacecraft. There are also electromagnetic forces due to a magnetic field. And we calculated that in the latest paper, given the charge of the spacecraft, how much of a deflection you would expect. It turns out the deflection is not negligible, but it's small. It's a fraction of an astronomical unit for the magnetic fields that you can imagine in the heliopause or along the path in the interstellar medium. It's not a big effect, but it's something to keep in mind. In addition to gravity, there are forces that are, and in addition to gravity and the friction force on the background gas, there is also the electromagnetic force due to the magnetic fields.
Okay, guys, I've noticed that people are saying that, I just got an alert that the YouTube stream is having some problems, but Twitch is going okay. So if you want to head over there, it might be buffering for you. Sorry, guys, I can't control it. It's between Joycaster and YouTube, and apparently YouTube is having some trouble. So I'm sorry about that. If you're having some issues. Okay, well, we're out of time, unfortunately. I've kept you 3 minutes longer than I wanted to, but I just want real quick to talk about Mike, and then we'll wrap this up. Once you get there, is the idea, Avi, to once you're accelerated to 20% and you get there in 20 years, is it to just fly by Proxima B, or is there any plan to decelerate, or what's when you get there, what's the plan?
Yeah, now it's very difficult to decelerate because you basically need a laser system on the other side that is exerting the same type of force that we are using on Earth to launch this system. So you can imagine decelerating on the starlight, on the light coming from Alpha Centauri A and B, but for that, you need to fly very close to the stars and you will get heated up. And you need a very thin sail that my wealthy friends to buy real estate on Proxima B. In the future, until we have a station over there or laser system over there, we have to just fly by. And of course, you may ask, why not build a huge telescope, hundreds of meters in size, a kilometer in diameter, let's say, on Earth, rather than send a camera over there? You could, in principle, achieve the same angular resolution. The answer is, for me, the thrill is really going there, because once you are able to launch things away from the solar system, it opens a whole new realm of possibilities. And frankly, I think it will be the biggest step forward that our civilization has made since the Apollo mission going to the moon. It will be a major milestone because, where obviously the life on Earth will not last forever, either due to bad, and we should just, this will be the first step of moving out of the solar system, which is a necessary step to demonstrate in order for us to enhance the longevity of our species.
Yeah, that was very well said. I couldn't agree more. Now I'm going to put you on the spot before I let you go. What do you have a forecast or a prediction for when we might be able to do this? Actually do the launch.
Okay, I can give 3 scenarios. One is the optimistic one that I'm very much hoping that will take place, but I'm not at all sure about whether it will take. My hope is that by the time that I'm in my 70s, let's say 2 decades from now, we have already built a demo and we are constructing the actual system. I will not see a photo from Proxima B in my life, probably, but I hope to see the construction of the final system. I mean, most of the cost is the infrastructure. So that's promising.
Well, Yuri's putting his money where his mouth is, right?
Right, but that's still 100 million. We need 100 times more.
Yeah.
So, but I think that's not the issue. The issue is really to demonstrate that we can achieve the technological milestones. And I think there will be a lot of byproducts that will come out of it, just like the Apollo mission. So I think the excitement, I mean, whenever I give a public lecture, many young people approach me with a lot of excitement and ask how can we get involved in this? And I think you get much more than the sum of the parts when a lot of people come together to work on an exciting, visionary project like this one. And that's the importance. I mean, you can always contemplate projects that are doable within a few years and are not pushing the edge, much. But in a project like this, you can get much more than you can imagine in principle, because there would be brilliant people that are excited, getting involved. And I'm thinking mostly about the young people. I gave up, I think creatively about the future. And I think the young people are really excited about this project. So that's my hope, that the younger generation will push it to fruition. And the next generation will benefit from this project and will bear the fruits of it.
Great. That's very well. Okay. Well, I hope you're right. And what I learned in this hangout, among a great many other things, and you and I are about the same age, so I'm also very excited about this. I'm not that pessimistic either. Jeff, any closing thoughts before we say goodbye?